Okay, we're going to go through the new material for IPv6 that was posted in 11.21, this being the bridge class. I think it's good to review this. IPv6 gets overlooked often as something that is something nice to know about, but isn't really necessary for your first job, most likely. And that's pretty accurate. So let's go ahead and move to a couple of these slides, and this gives you an idea of what we're going to talk about in this section and what they're asking you to know for the new CCNA exam. They want you to be aware of the IPv4 issues, how to represent an address, how to drop those leading zeros and use the double colon. We'll get into that. The two different types of addresses, so the global use and the link locals. How to statically configure those, and we'll do a couple of labs on those. And then how the dynamic configuration works. And they dropped a little bit of the DHCP stuff in this section. We'll kind of pull that in as well. That's pretty much the same stuff there. So first thing is first, this isn't any different than what was in the last version of CCNA. IPv6 is a protocol that is available and can be used. The hierarchical structure for it is a little bit better than what we had for IPv4. So when you think about how an IPv4 address is pawned off to an internet service provider, it was just first come, first serve. So no one had any idea when they came up with IPv4 and it became public domain that the world was going to start utilizing it as a marketplace and a service destination for all kinds of things. They just kind of were like, oh, this might have some impact. And so if you maybe had an internet service provider and you were in the United States and you got an address range and you got everything that started with 7, the range that started with 8, maybe you could have been in Africa, and the range that started with 6 could have been in Australia, and it really wouldn't have mattered where those ranges are at. In IPv6, that's not the case. So each one of the governing bodies, and they get a nice map there that shows each one of them, they get their own prefixes. So for instance, in the United States, pretty much everyone's going to start with 2001 for now, or at least I shouldn't say United States. Let's open that up to all of North America. So in all of North America, you're probably going to have a 2001 address because those are the addresses that were assigned to the United States. If you're in South America, it might be 2002, Africa 2003, so on and so forth. And makes it the routing really, really easy as to where the source of the traffic has started from. So keep that in mind. That's all they're getting into in that slide. The next slide talks about coexistence between IPv4 and IPv6. There's a few bullet points on here, and really the fact of the matter is there isn't a really smooth way to have something that's addressed in IPv4 and then encapsulate that inside of an IPv6 address. There's a few methods that are listed here, and really the downfall, I wouldn't say, no, maybe the downfall is a little early to say downfall, but the reason that the IPv6 hasn't really been accepted is IPv4. We just figured out how to make IPv4 work correctly just a few years ago. So to switch everything over to a whole new IP addressing system when the old one is still working pretty good, even though we're running out of addresses, and we have been for quite a while, you're now looking at changes in addressable structures that may not be totally understood by as many people, and it could cause failure, and it could cause outages. And we just got to the point where we're really not having that many outages anymore. So it hasn't been really embraced by the community. There are 3 methods that they list here that you can use for coexistence. One of them is called dual stack. That's basically like closed captioning, right? So people are talking, but you're also seeing the words. So you've got 2 different methods you can use to figure out what's being said. Both IPv4 and IPv6 are being used simultaneously for all traffic. So you're bilingual. You're sending everything on two different addressing schemes. That's fine, except for you're using twice the bandwidth when you do that. Tunneling is a method that you can use to encapsulate IPv6 into IPv4, or you can go the other way. You can go IPv4 into IPv6. Both are good methods. They do slow things down, and they add an extra header. So it's a little clunkier. It's going to be a little slower. You're going to have more overhead. And then there's translations where you can do network address translation, where we'll translate an IPv4 address into an IPv6 address, or IPv6 into IPv4 for your usage across the internet. So instead of doing a NAT translation table with just IPv4, you would do it with IPv6 on one side. So that is an option. None of them are really being used all that much. So just got to keep that in mind. The next section that we get into for IPv6 is the section that gets into how to write an IPv6 address. The addresses are really long. We just got used to thinking that a 32-bit address is a pretty normal looking thing. And then we have to have another 32-bit address that goes along with that for subnet masking. And it's fairly complex. And then we take that and then we extend it to something that looks like something no one would ever want to write in their life for IPv6. So if you look at the formats at the bottom here, where it says preferred formats down here, what we've got is, we've got addresses starting with 2001, and then we've got 0 dB8, and then quad zeros, quad ones, quad zeros again, quad zeros again, and then 0 to 100 for this first address. That's all well and good, but we can truncate this and we can shorten it down into a shorter format. We'll do that in the next slide. But if we think about what we've got for any given address, and this is really 1, 2, 3, 4. What you want to think about here is that you're going to split that up, and what's cool, the only thing that's cool about IPv6, I did not just say that, is of the 128 bits, for any given host, we're going to do 64 bits for client and 64 bits for network, and we're going to split it right down the middle. We don't have to worry about subnetting on LANs because our LANs are 2 to the 64th power big, and that's just way bigger than any LAN is ever going to be. So we will do some subnetting when we get into passing from router to router, because you can hierarchically update things. But as far as a host goes, your subnet mask is always going to be /64. So that's pretty cool. All right, let's move on. Rules to truncating your address space. And they've got a few of them listed here. Anytime there's a leading 0, we can drop it out of a sextet. So if we've got 01AB, you can just drop that leading 0. If you've got 09F0, you can drop the leading 0. What about the closing 0? No, you can't, because then you don't know. If we drop the closing 0, we'd end up with 9F here, and you don't know if that's 009F or 09F0 or 9F00. It could be any one of those, and if you don't know, you can't. So just the leading 0 can get eliminated. So that's what they've done here, is they just eliminated that leading 0. The trailing 0s, not so much. Same thing on the next two, and that's a way that you can truncate things down. So you can look at what they've got down here, and they've dropped all the leading 0s out, and they've taken this 2001 address and shortened it down significantly just by dropping the leading 0s. Now in the next slide, we're going to go one step further, and we're going to find if we find hextet values with zeros continuously, we can drop those out with a double colon. Okay, so I guess we can just go all the way to the bottom on this one. So if we've got 2001 0 dB8, we can obviously drop that leading 0 there, and then we've got a block of 4 zeros here, and then we've got a block of 4 zeros here, here, and here. Now the shortest way to write this out is we can take one block of quad zeros and we can replace it with double colons. Basically saying this, that we know that there's going to be 8 parts to any given IPv6 address. So there's 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 blocks. Now, if we take the 3 sets of leading zeros and we take them out, we're going to end up with just 5 blocks, and we'll know that the double colons represent 3 of those blocks. So that's what they did here. So they went to 2001, DB8, 0 here, 0 for this 0, and then 1111, and then they double coloned out. This double colon represents all 3 of these blocks. Now, how do I know there's 3 blocks there? Because I'm left with 5 blocks, right? 1, 2, 3, 4, 5. 5 blocks. That means that whatever's missing has to be 3 sets of zeros. Easy enough. Could we write this the other way? Could you do this as 2001 : DB8 double colon here and double colon out this piece, and then finish it up with 1111 : 0 : 0 : 200. Yeah, you absolutely can do that, but it's going to be shorter if you use the double colon for multiple runs of hextets with quad zeros as opposed to just one of them. So if you look at it this way, now you've got 7 blocks instead of the 5. So 1, 2, 3, 4, 5, 6, 7. Hey, we're only missing 1. I know that we're missing 1 because I know it's going to add up to 8. Simple arithmetic on this one. Okay? Easy enough. The next thing we're going to get into are the types of addresses for IPv6, and we'll just go ahead and continue on this slide. There are unicast, multicast, and anycast addresses. This isn't that much different than what we did previously, except for you'll notice that there are no broadcast messages. So where there used to be broadcasts, there are no longer any broadcasts, which is a little bit weird. We've just replaced them with multicast, and anycast is something that's it's not new, but the use of it is still a little up in the air as to exactly how that's going to work. Unicast traffic is pretty straightforward. I have the IPv6 address of a device that I want to communicate with. Easy enough. I'm going to put that in the destination IP address field for an IPv6 header, and I'm going to send it on. Multicast, a little bit different. So in multicast, and what we've done with multicast is we said anywhere there was a broadcast message before, we're going to add a multicast value to listen for this type of information, and if it is received by a device that has that multicast address listening, that device is going to respond. So it's a lot like broadcast, but it's not. It's a multicast address. Let me give you an example. A good example of where we use broadcasting is in ARPing, right? So when we ARP for something, we've got the IPv6 address. What we don't have is we don't have the MAC address of the device that we're looking for. Okay, well, not a big deal. What we can do in IPv6 is we can send out a message called a router solicitation, also known as an RS, and we'll receive back an RA, which stands for a router advertisement. We can also do what's called an NS, or a neighbor solicitation, and receive back a neighbor advertisement. Now, how is this different than broadcast before? Well, the thing is, routers are listening on the multicast address for router solicitations. They're listening here. Routers are listening here. Hosts are not listening for those particular router solicitation messages. Neighbors, other hosts, are going to be listening on the multicast address for neighbor solicitations. So what have we figured out? Well, we've gone from a broadcast system into a multicast system by separating out devices by type. And that's all that's really happened there in that change. So when a device is looking to resolve an IPv6 address into receiving a corresponding MAC address for that device, because we still got to pass through the switch, right? We're gonna send those messages out by type of device. Is it for a router? Is it for a neighbor? And that's a good example of what's happening with how they've eliminated broadcast messages by adding multicast and stylizing it by type of device. Okay, so just keep that in mind. So unicast, multicast, and multicast works, same as it did in IPv4. And then the Anycast is a way that you can look for services no matter where you are. So, like I said, it's not totally proven, but a good example would be like if you were on like a mobile phone and there was a specific service like 911 that you're always looking for. You could have an Anycast that would say, I'm in a new zone. I'm looking for my 911 services, and the 911 services in any place in the world would respond back, and you don't have to do anything to make that work. It's just that service has a statically configured address that will give you that service no matter where you are. Okay, so that's a little bit of what they're getting into there. Now, the next part is something that we had talked about already. The address is 124 bits, and any given host is going to end up in 64 and 64. So you're going to have a 64-bit network prefix, you're going to have a 64-bit host address, and that's the way we're going to split it up for hosts. Now, there's a whole bunch of different ways to design that host address. You can hard-code it in yourself. You can use different algorithms to have it built. Some of the slides in here talk about a method that you can use, EUI64, that will take the MAC address and break it apart and flip a bit. These are all things that you can do, and you can have it happen automatically. And that's pretty common and pretty normal that's what you'll see for these types of addresses, that they will be manufactured without the use of a DHCP server and without you having to statically configure your IPv6 addresses. So that's something that you are going to see. Now, of those addresses, there are going to be two different specific types, and every device that connects to the internet is going to have two addresses. Each device is going to have a global unicast address. These are the ones that start with like 2001 in North America, and this is an address that you're going to learn through. Either you're going to statically configure it, or you're going to do what's called a router solicitation, and you're going to ask your router. You're going to say, hey router, I want to get on the internet. What is the prefix of this location that we're at right now, so that if I send something out on the internet, the networking portion will be consistent and the response will come back here and I'll be able to communicate on the internet. So the router solicitation is going to identify what that prefix is going to be. Now the network portion, the host portion of that is going to be determined based on one of those other methods we learned for building the host, either statically configured or an algorithm that's used to determine the host value. Could be EUI64, could be something different. But you're going to have a unique 64-bit host value that's going to sit behind that 64-bit network value that you're going to have at that location. The other thing that you're going to get is an address called a link local address. Now, there's a lot of space for link local addresses, but the link local addresses that we're going to use are going to be FE80. Whoops, get rid of that. FE8. I'm looking at that. I'm like, that's not correct. They're going to start with FE80, and then they're going to generate your host 64-bit address that's going to sit right behind that, and that's your link local address. Your link local address is what you're going to use to communicate to local devices. So what are you going to use to talk to your router? You're going to use your FE80 address. What are you going to use to talk to your other neighbors? You can use your FE80 address. So that's an address that you're going to have, and it's going to be used for local communication. It's analogous. Instead of like taking like the private address ranges that we have in IPv4 and saying, oh, we got 192.168, and we've got 10 dot whatever, and we got 172.16 through 31. let's just go with one of them. Let's just go with, it starts with FE80, and that's your link local. That's your private address range. And if you're going to be confined to a private range and not use IPv6, we can just turn our router solicitations off, our router advertisements off on our routers, and we'll just never get a 2001 address or a global unicast address at all. And you won't participate on the internet with IPv6, which is, it's something that it's done. That's how we do it in the classrooms at COD. So just keep that in mind. This just talks about the unique local addresses and the fact that the range starts from FC00 to FDFF, but FE80 is the one that really you're going to end up seeing all the time. So keep that in mind. And as far as the global unique addresses, this just kind of lets you know that every global unique address has to start at this point. Because there's so many addresses with this space, they're all going to start with a 2 or a 3. So to be a global unique address, it's going to begin with a 2 or a 3. Like I said, most of the time in North America, 2001 is what you're going to be looking at. I think we get 2008 as well, but I can't remember. Don't hold me to that. And don't distribute this video if that's wrong. If it's right, yeah, go ahead. So 2001 is what you're normally going to see as your kind of your public IP address space. It's going to start with a 2 or 3. Generally a 2 right now. IPv6 still not off the ground yet, and it is a massive, massive space of addresses. So keep that in mind. I think we've talked about that slide. This talks about link locals. We've talked about this. This is a nice slide. This is a good little diagram here where I guess I'd rather start, well, whatever. We'll do with one. Router to router, going to communicate with each other with link local addresses. And this does bring up another point as well, is the routers will have link local addresses also. And in the labs, you're going to hard code those. And so for a device like this, it's going to have two interfaces. It'll have a G0/0 and a G0/1. And in both cases, what you're going to end up doing is, let's say this is router 2. We would say this is going to be FE80:2/64 on G0/0, and then on G0/1, we're going to put the exact same address on that interface. So one of the rules of IPv4, which is never duplicate an IP address, just throw that right out the window in IPv6. We'll go ahead and use as a general standard, we'll put the same link local address on every interface on a router, just so that we know we can identify where it's at on the network. So that's something that can be done and is done in the practice of the lab. So you'll see that in the lab and you'll be like, am I allowed to duplicate IPs? And the answer is actually, yeah, you're allowed to duplicate IPs. So keep that in mind. Here's some static configuration right here. Pretty straightforward. You'll do that in the two labs that I'm going to assign as well. Go ahead and statically configure an IP address as they've done here. You'll do it on hosts as well. And you'll configure also link locals, and we just kind of went through the weirdness of those. So just be aware of that. Stateless auto configuration with DHCP. This is really the last thing that I want to get into as far as this chapter goes. And what it comes down to is this. If you think about an IPv4, in IPv4, your DHCP server is going to give you an IP. It's going to give you a subnet mask. It's going to give you a default gateway, and it's going to give you a DNS server. Okay. Now in IPv6, we go, you know what? Oops. Hey, come back here. Go back to where you were at. In IPv6, you can generate your own IP address automatically, so you don't need one of those. And in IPv6, the subnet mask is going to be a /64. And you don't need one of those. And in IPv6, the default gateway is going to come out as through a router solicitation. So you don't need one of those. So in IPv6, really all you need from DHCP is quite possibly a DNS server, and that's all you're going to get from your IPv6 DHCP servers that are on your network. So I'm using a native IPv6 network device. I show up at this location. It's using DHCP. My device self-configures. It gives itself its own FE80 address. I know it's a /64. It does a router solicitation and gets a 2001 address on that network, and I'm ready to communicate on the internet. Now, what I don't have is a DNS server that maybe works, because maybe there's some firewall rules that say only certain DNS servers are allowed to be used on this particular network. In that case, a DNS server would be passed along to my device, and I would be able to then communicate on the internet. So the role of DHCP is shortened for the most part in IPv6 to just handing out usable DNS servers. So keep that in mind. That's really the main point of everything they get into is on those pieces. The EUI64 process is a way to randomly generate or create a host value for a device based on its MAC address. And they do a nice job of identifying that. If you look at not that one. I guess this one here. So you can see, EUI 64. We're going to go ahead and take the MAC address. We're going to flip the 7th bit, and then we're going to pad it out with FFFE in the middle, which is going to, I don't know if you guys can see that or not, FFEE, because our MAC address is going to be the 48-bit address. It's going to be 48 bits, and the host portion for IPv6 is equal to 64 bits. So that being said, there's 16 bits of padding that need to be added. And those 16 bits of padding end up as F, 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 E. And they just throw that right in the middle. So they take the first 24 bits of the MAC address and move it to the left, and then they put FFFE in the middle, and then we take the last 24 bits and we put it to the right, and there's your EUI 64. Oh yeah, flip the 7th bit from a 0 to a 1. That's it. That's a method that you can use. Does Microsoft use that? No. Does Cisco use it? Yeah, you can use it. You can use it on your routers if you want to. That's pretty much all I wanted to go through as far as this goes. The next section, what we'll do is we'll pull out the 2 labs that I'm going to assign you for today, and I'll have those posted before the end of today, but not this morning. So I hope you enjoyed the video. Please watch it before class. I should have said that at the beginning. And then we'll have a forum at 1 o'clock, or we'll call it 2 o'clock. Okay, sounds good.